Okay. Welcome to all. Welcome to my students and subscriber and professionals. Today I am going to discuss one very specific problem for the estimation of overall heat transfer. Okay. So the problem is, say there is a fin tube. Let me tell you. Say I am drawing a 2D axis symmetric. Say there is a stem and in between there is a annular path, and in the peripheral side, means the outer side, there are some fins, and let us consider some hot fluid is entering through this annular path and it is exiting out. So definitely the heat will be evacuated by this arrangement or this geometry, and definitely you will get a, if you take the temperature along this, if I plot, so you will get a profile like this. So say I want to make one analytical formula to estimate this curve. It's not so simple, correct? Because what basically happening here, so if we see it briefly, means in elaborated way, say heat flow is taking place in this direction. So say this point is A, this point is B, this point is C, and this point is D. So A, B, C and D. So the liquid temperature here, if we see now here, if we plot the liquid temperature, it will be coming like this, and after here it is following another gradient, and after coming here it is following another gradient. Why so? Because the temperature gradient we are obtaining here, that means in the liquid, which is caused by the convection, that means the liquid to metal, and this line is basically metal to metal, so that is due to conduction. But here again heat is evacuated through air by convection. So this blue line is representing that. Now to obtain this profile, we need to estimate the overall heat transfer, correct? Overall heat transfer, which is very difficult because the geometry is complicated. We cannot apply because here conduction is quite easy, but for the convection, means the convective heat transfer coefficient, it's not constant. it's dependent on the flow as well as the temperature. That means if the temperature, the object of the temperature is high, the heat will be evacuated with higher rate. Okay, and if it is temperature is low, then the heat evacuation means heat convective heat transfer rate will be less. If flow is more, your convective heat transfer will be more. So definitely this area, this is natural convection. Okay, so we have to estimate that overall heat transfer coefficient, the overall heat transfer for this arrangement. So how to do that? So to start all these things, first of all we should understand the concept of thermal resistance. So let us first draw a electrical circuit. So this is my resistance and the current is flowing through this I, and this is my potential. So the electrical resistance as per the Ohm's law, which is V by I, is very simple. So V is the potential difference. That means this is the factor which is causing flow of electron, I. So in thermal circuit, if we try to equate it from this electrical circuit, so the heat flow is causing due to temperature difference, and I is a flow of electron, and here it is a heat flow, so that is Q. On the other hand, Q is equal to delta T by RT. Okay, so what I mean to say, this RT is, we'll see that things in later, this RT is quite constant when the conduction is taking place, but in convection this is varying. We can do another exercise. Say for Newton's law of cooling, so this Q is equal to HA delta T. Now I can write that delta T, Q is equal to delta T by 1 minus HA. So now this equation and this equation, if we compare, then my RT is equal to 1 by HA. So it's a very standard formula for convective heat transfer. If I know the convective heat transfer coefficient and the area through which the convection is taking place, then the thermal resistance of convection is given by 1 by HA. Now similarly, if we try to find it out for conduction. So you know, conduction is basically based on the Fourier's law, minus Ka dt by dx. Now here this portion, if I consider this portion, basically this portion, through this portion only pure conduction is taking place. And you can see this is a cylinder. If I draw it, it is like this. Say the length is L and this diameter, this radius is R1 and this radius is R2. Now I am considering one small segment, these things, which is dr. So now simply the dx I can replace by dr. Okay. Now for this, the area, the surface through which the convection is taking place, through this area. So this is nothing but 2 pi RL. So minus K is the thermal conductivity, 2 pi R L dt by dr. Now if I rearrange the equation, Q into dr by this R I am taking down, which is equal to minus 2 pi K L dt. So now if I consider the temperature at the inner surface is T1 and this is outer surface is T2, then if I do the integration from R1 to R2, this will be from T1 to T2. It's a very simple integral. 1 by R means it's a log. So Q into natural log R2 by R1 is equal to, this minus is there, so 2 pi KL into T1 minus T2. Okay. Now what already we learned, the resistance, the thermal resistance due to conduction, I am giving the name, which is del T divided by Q. So here del T is this one. So del T by Q, that means T1 minus T2 by Q is nothing but this by this. Alright. So this is natural log R2 by R1 divided by 2 pi KL. K is the thermal conductivity and L is the length. So this is the formula for calculating the thermal resistance due to conduction. Convection already we obtained. Now coming to the point, to find out the temperature distribution along this liquid which is flowing through these annules, what is happening basically? So there is some resistance is offering by this boundary, means here it is going from liquid to solid, which is convection. So that is your resistance, say R1. Then it is flowing through the solid, so that is R2. Again from here it is solid to air, that is R3. So this is your overall thermal resistance. This is to be estimated. this is to be estimated. Then only if I able to find out this, and if I know the temperature of liquid here, and the temperature of the solid here, and this R is known, then the overall heat transfer rate is del T divided by this R. Then only we can estimate it. But it is not so easy, as I told. How we will estimate? How we will estimate the value of H here? Basically, if I want to elaborate this, that is 1 by HI. Inside I am telling AI. But this is very easy. Natural log R2 by R1 divided by 2 pi KL. It's constant. You see this thermal conductivity. It's a passive parameter. Length. This length. This is also a passive parameter. R1. This is R1. R2. This is R2. Those will not change. Those all things will not change with respect to temperature. So this R2 in this case will remain constant. But R1 and R3, what is R3? R3 means how the heat flow is restricted through this area. So which is 1 by H out, A out. So which is involved this unfinned area and the finned area. So how to find out this overall heat transfer coefficient? Overall heat transfer rate. So today it is very simple. You have to do the analysis, that means in CFD, conjugate heat transfer. So where the coupling is, so conjugate heat transfer means the heat transfer with flow. So you can use SolidWorks, COMSOL, ANSYS, whatever may be. If some other packages are there, I can't remember right now. So first you take the laminar flow as well as the heat transfer, and you couple these two analysis and find out the temperature distribution along this path. So as I told earlier, you will get a temperature profile like this, that is the temperature gradient in the liquid. Then you will get like this, that is the temperature gradient in the solid, and then you will get a temperature like this. So this is in the fin area. So say this temperature is T1, this temperature is T2, this is T3, and this is T4. So from this analysis you will get every segment delta T. Now as I told, this area is happening, the heat transfer is due to conduction. So the resistance is offered by conduction. So which is, that means the R2. So we can consider that is constant irrespective of temperature. So from this delta T and R2 you can estimate during applying the formula which is natural log R2 by R1 divided by 2 pi KL. Using that you can find out this Q. And I can here the assumption is the heat transfer, it is happening in the as it is in series. by neglecting the contact resistance, okay, not neglecting, we are not not considering the temperature drop at the junction, at the contact. Okay, so from this area you will be able to find out the Q. Now if I get the Q and if I want to calculate R1, so which is nothing but T1 minus T2 by Q, and R3, that is T3 minus T4 by Q. Okay, so once I got all the three, if you add it, because as it is in series, you will get the overall thermal resistance, and you know the liquid temperature in the anodes as well as the temperature at the tip of the fin from your CFD, sorry, conjugate heat transfer analysis. Now the overall heat transfer Q, that is equal to T1 minus T4 divided by R. So this is a technique through which, by using the simulation as well as the simple mathematics, how to find out the overall heat transfer for complex geometry where the Nusselt number cannot be estimated using conventional regression formula, because the characteristics length is not known. Okay, so this was all about the discussion of today. Anyway, a detailed book is getting published on this soon. So once the book is published, I will provide the link in the video so that in details it is elaborated there. Okay, so thank you so much for watching.